Okay, so thank you for being here. I'm Falcou. I will speak about SIMD programming and how to actually design meaningful C++ libraries that deal with this kind of programming paradigm. So I'm working at Numscale. I'm actually the CTO. We are a small French startup which specializes into bringing C++ library for performance to users into the objectives of actually simplifying the use of modern hardware. We are also pretty much involved into C++ to the ISO committee and our contribution to different open source projects and other community-like activities. So let's speak about what we want to speak there, which is what is SIMD programming. So let's start with a simple amount of questions. So who actually deals with performance issues as a daily, constraint in their jobs around there? Okay, pretty much everybody. Cool. So who knows about parallel programming in this subset of people? Well, pretty much. Okay. And now let's try to focus on who knows about SIMD programming already. Okay, so I probably have to be careful what I will be saying. And so who actually use something like this kind of stuff in jobs? Okay. And actually who has nightmare because of all those? Yeah, okay, fine. So for the few people that are probably not familiar with SIMD programming, let's have an actual small metaphor about what we are dealing with. So let's say you have some amount of data to process, okay? And what you have first is a simple normal CPU, okay? Nothing fancy. So whenever you process your data through the CPU, every cycle you get the results, okay? So you get some amount of cycles before getting your results. So it can be quite long, especially if the processing is rather regular. It could be cool if we could actually process more of the same data, a bit faster. So the idea is to get a different version of your regular operation that we will call a SIMD-enabled CPU, okay? It's a bit different. It looks like the first one, but it's a bit bigger, probably a bit more cumbersome to handle, but every cycles, well, you get more results. So basically, if I want to get back to something a bit more technical, SIMD instruction set inside CPUs are actually dedicated systems inside the CPUs that will process what we call wide register that can store more than a single value at a time, and then we get processed by a single instruction every cycle. So every data in the wide register will be processed with the same instructions, and we end up with the same amount of outputs in the end. And usually those special registers are processed using special instructions that may or may not have a human readable name. Most of them don't. And there is a kind of general process. I'm using the Blitter terms, which is something that was coined back in the 2000s by, what is his name already? Some guy from Altivec, which means that you have data coming in a regular way. You will apply this regular pattern of instruction set on all your data the same way and get your results. So the idea is, as we process more than one data per register, per cycles, we expect somehow to get a speed up, which should be roughly related to the width of the vector. So we want this speed up of something that looks like n if everything is perfect and correct and whatnot. And this additional performance that you can actually extract from basically every processor out there may bring some additional ×2, ×4, or ×10 that you need to get your application up to the correct speed you need, okay, without having to resort into scaling out or getting more cores or whatever. And by using this specialized instruction set, you will also be able to maximize the flops per watt metrics, which is, in some cases, a very interesting optimization. So we are dealing with some hardware-specific systems that actually speed up your code by processing more data per cycle than the regular one. Sounds like what a GPU does, but it's not quite a GPU. That's inside your processor. And if I want to go back to this very funny culinary metaphors, well, if the SIMD expression set in your processor is this very large knife, well, a GPU is more like a huge potato slicer with a very thin grid, okay, this big, and you cannot exploit all the power processing of your GPU unless you have a perfectly sized potatoes, okay. So SIMD computation is a form of data parallelism that also have an impact on how you can write low latency algorithms. It's not restricted to huge amount of data processing. So the question is, how do we actually, what is actually available? That's a very small subset of what's probably available right now. We have, I don't know how many x86 based instruction set right now, ranging from the very, very old MMX 64-bit systems up to the AVX 512 most recent 500-something bits extension set with a lot of intermediate variants, more or less code-dependent or complementary across SSE2 and AVX and so on. We've got a bit less such instructions on PowerPC, with mostly the VMX, VSX systems, the QPX, that was the 512 bits wide register for BlueGenQ. And of course, we have SIMD instruction set into ARM, mostly through Neon and the 64-bit versions of the ARM processors that bring us double and 64-bit integers to the mix. So I guess that most people actually know about this, actually focus on the subset of all of this. The most classical usage that we saw in the wild is people using SSE2 to try to speed up some codes. Some try to dabble into using AVX. Well, I don't know, many people still try to use Altivex systems, but there's probably a bunch in the wild somewhere. And another very popular one is obviously all the mobile application using the Neon instruction sets. So it's quite problematic if you really, really want to have an application that goes, not saying everywhere on this list, but on the subset, which is meaningful without having to redo your code every time. So how can we actually take advantage of those SIMD instruction sets? So the classical way of splitting this is to see on one side what we call implicit vectorization. Will be basically relying on the compiler's capabilities of finding subset of code which are candidate to vectorization, and on the other side, explicit vectorization through language extensions or libraries and so on, using the vector intrinsics, we will get to that at some point, or inline assembly. And just because if not, we probably won't fit into 1 hour, and I don't really want to dabble into that, let's all agree that we will say no to inline assembly anyway. Okay, I got only so much sanity left, so. Okay, so implicit vectorization. Well, the point is to have the compiler analyzes whatever your loop nest is or random code is. You can actually try and help the compilers by using ints that could be keywords like restrict. We can go back on that a bit later, or pragmas, or a combination of those that will help the compiler know that, you should really take into account that this loop nest or this function is maybe something you can vectorize. But the compiler is always have the final word for that. So if it decides that the transformation is not safe in terms of results or other constraint, it won't do anything. So you have these restrict keywords, which is a way to tell the compiler that you put your right hands up and you swear that this pointer A and this pointer B don't alias. So they have no overlapping zone of data between A and B. So the compiler is free to optimize as much as it can about the memory access to these pointers. And this pragma is an interspecific pragma. I would say, yeah, there is dependence there, which are actually regular dependencies in a vectorizable loop, so you can actually try to vectorize. So the compiler can find these ints, run a very complex set of compile time analysis that could be very simple, up to stuff like polyhedral models that will turn your loopness into a multidimensional representation of your loop into polygons and do fancy math stuff on it, and then generate the correct code afterwards. But at the end, if the compiler thinks that transforming this code into a vector code is unsafe for some reasons, it won't do it. This actually gets great results in most of the trivial cases and some non-that trivial cases around. But the problem is that you are tied to the quality of your compilers, the quality of its, let's say, its vectorizable patterns knowledge, and the fact that you really don't think that you should not be doing this. So when it works quite well, and a large bunch of code can actually be automatically vectorized using this kind of stuff. But when it does not, you're in the blue. So on the other side of the spectrum, we speak about explicit vectorization. One of these is, for example, what you can do with OpenMP4, which is the latest OpenMP standards. The idea is the same way you flag loops to multi-thread them, you can flag loops to say, hey, this loop, I really want you to make a SIMD version of that. OpenMP4 also supports reductions, like in this example. You can flag function as being something that if you call it later, you can also get there and vectorize what's inside, and so on and so on. But contrary to auto-vectorization, you are in charge of applying those pragmas where it makes sense. So if you slap a pragma OpenMP SIMD somewhere and the loop makes no sense to be vectorized, the compiler will probably generate codes that make no sense either. Okay. And then again, when you are actually be able to use that, get a good quite bit of performances on a subset of actually interesting cases. There is a lot of stuff going on because you can actually specify what kind of vector width you want on a given loop nest, what kind of dependency you want to carry on, and so on and so on. So if you want, you can actually dig inside the OpenMP4 documentation. There is a lot of things you can do with this kind of pragma. So that's another way to do it. Then again, you need an OpenMP4 compliant compilers, and you're basically again at mercy of what the compiler is able to do and the quality of its implementation. People also try to wrap SIMD computation as a library. Most systems provide intrinsics and special types that maps to the SIMD registers and the ways they have to be handled. And you can actually just wrap that into a properly named structure and use parallel overloading and so on and so on. And you can actually try to wrap some very specific SIMD items within algorithms or other adapters and abstractions. And it's actually helpful because you can actually improve portability across compilers, because at the end, you will just call whatever is the lowest level way of accessing those registers. There is a bunch of them. I'm just citing a bunch. There is the Agnes Vox x86 library. You have VC by Matthias Kretz, Nova by Tim Benchmans, GSIMD, which is an effort made by IBM, and SIMD, which is more or less a SIMD library with a focus on data structures. It has fancy array of structure of array adapters, which is quite cool. And you have BoostSIMD, which I will be speaking about a bit later. So, and then you can use intrinsics. Okay, sometimes it's okay. I mean, this is how you make a 32-bit integer multiplication using Neon. Okay, so you have two flavors of Neon. You can use small and less small registers, basically by putting a Q or not. Okay, so I see we have two vectors and I just vmule them. Okay, fine. You can do something that looks like this using the SSE4. So the naming is different, but you still kinda sort of guess what's going on. And well, sometimes, you're on this road and everything is fine, and you just get out of the road. So I'm a bit pushing the examples there, but because normally if you use GCC, you could actually just use the multiplication operators and you don't have to write this kind of crap. But just for the example, yeah, that's exactly what it looks like. It's a multiplication between two 32-bit integers. Okay, I guess everybody saw the algorithm which is used there. It's perfectly clear. Well, back in the day, I had to write that by hand. It took me like, I don't know, probably a week or so to get it working right, but whatever. So, well. And it's no better if we go back to the good old AltiVec. It's a bit less contrived, but it's still a bunch of code to write. Yeah, so I'm actually very pushing the envelope there. Most of the time, it's not that bad. Could be. And you don't really want to have a piece of code like that in the middle of nowhere in your code base, especially if you have to maintain, you know, some kind of homogeneity in the complexity of your code base. You may argue that, yeah, we can slap everything into a macro and call it a day. Yeah, it will be okay for a bunch of them, but quickly it starts to be a bit cumbersome. There are still cases where it's actually helpful to go at that level, but normally you should not. Okay, so yeah. So, and as I say, I won't speak about inline assembly for a lot of reasons. There is another bunch of tools you can use. The one I didn't speak about because Nicola Gizmo is making a talk about ISPC when? Tomorrow, yeah. So and it will be probably better than me at explaining all the cool things that ISPC can do. So in a nutshell, what we have at one side is we can actually rely on the compiler being able to implicitly vectorize your code. And sometimes, we actually probably make an example later where you can actually see that it's getting a good bunch of performance. Implicit vectorization is only as good as the effort that has been put into the compilers, but they are getting there for most of the trivial cases. You still have issue with having non-inline function called in the middle of a vectorized loop. You have a limited support for outer loop vectorization, which can be something which is useful sometimes. But when it works, it works. Okay. And on the other side, the explicit SIMD vectorization, so you have to do the work of is this loop actually vectorizable or whatnot. You don't have to need data dependencies analysis to figure out what's going on. You can vectorize non-inline function in some cases, and if you want to put some efforts, you can actually also vectorize outer loops. And it's a bit more portable across compiler in terms of performance. And I mean, when something compiled with an explicit vectorization scheme, yeah, you pretty much know that something gets vectorized. Relying on the auto-vectorization may lead to code that may or may not be vectorized for some reasons. There was a funny old story at the very beginning of auto-vectorizer in GCC where someone was actually complaining because he has a loop which was basically A of I equal B of I times 3 dot. It was table of double. They get vectorized, and 10 lines later in this code, you have something like A of I equal C of I times 3 without the dot. And the compiler was saying, okay, you're multiplying your double by an integer. I don't want to vectorize that. And people were scratching it for weeks until someone said, hey, what about putting a double there? But well, now we are hopefully far from that. I mean, ICC, for example, has probably the most impressive list of vectorizable patterns. It's a very nice piece of compilers that do a very good work. But sometimes you're stuck into places where the compiler doesn't want to vectorize and you don't really want to write intrinsics or whatever. And so we need something to go further than that. So what we decided to do a bunch of years now, yeah, a big bunch of years actually, was trying to find a way to have a modern take on those, let's make libraries that wrap intrinsic and so on and so on. We tried to do this. We get somewhere some years ago, and the state of where we ended up was not that good. So we decided to scratch everything and rethink about the problem. And we finally found a better way to rework this library. And what we did actually was, build this SIMD programming library that we call BCMD, which is one of our closed source software, which is basically one of these explicit SIMD library, works a bunch of architectures everywhere, x86, PPC, ARM, and we have some domain-specific algorithms which are pre-optimized. And what we decided to do is actually take a bunch of this closed source software and turn it into an open source library, which is now BooSIMD. And the open source version is basically limited to x86 and Power, and have a bunch of standard-like algorithms. So you can actually play with that and try to see what you can do. So I will spend a bunch of time trying to demonstrate what we can do with that, and we will dig into the implementation tricks a bit later to see how we can actually manage to get there. So what we decided to do is to have a very simple abstraction, which is the what we call the pack, which is an abstraction around wide registers. So basically, it's a regular value type. You can use like every other standard types. It wraps a block of n elements of type T, which are contiguous. And depending on T and n, the storage of this pack of data will be different. And if you don't really know what to put for n, you can just omit it. And at compile time, we will pick up the optimal width of your pack, depending on your architectures. So T as currently needs to be a fundamental type, so integers, double, whatnot, everything except bool. We have a special type which is called logical that we use to handle Boolean values. I will get a bit over that, why we need a special type for Boolean a bit later. And n must be a power of 2. Could be 1, not very useful to have a wide register containing one element, but it's actually required for, the whole generosity of the code. And so what happens depending on T and N? Well, let's say we have C, which is a current hardware optimal register size for a value of type T. So let's say you are on an SEC machine, you are dealing with float, so C is equal to 4. So if you make a pack of this size, we will just directly use the native register types. If it's bigger, we will store an aggregate of 2 packs of the same type, but half the size. So this size may be still too big for the regular register, and we will keep doing this aggregate of 2 down, up, we end up at this point. And if the width you request is smaller than C, currently we fall back to an array of scalar value, which have been proved to be not that optimal, so that will probably be changed in the next release to use a native register and use masking operation whenever needed. So basically, either you have the native register you want, or you will have a succession of, let's say, intermediate representations that will end up aggregating the proper number of native register. Having a width which is greater than the natural cardinal could be actually useful on some systems, because basically whenever you do operation of larger than required pack, the side effect of doing this is basically we locally enroll every operation for every sub-element of the pack, which can actually be useful to get some performance back in some cases. So, but when we choose whatever is going on, depending on T and N, we got something which is as close as possible to the optimal storage we need. We take care of alignment and so on, of course, so everything is set up as it needs to be. So what can we do with a pack? Well, first, maybe we can try to see if we can put some data into it. We have a bunch of constructors, the classical splat constructors that will fill the vectors with n times the same value, or you can actually curly brace initialize it with a list of scalars. You can pass it a pointer, and it will perform an aligned load from these memory addresses. Or you can pass a range. And it could be an actual arbitrary range, not necessarily a contiguous one. And we use tag dispatching inside on the iterator category to know the best way to actually fill our vectors with this range. So if we find out it's actually a random access iterator, we do the proper numbers of access, same for the other ones. Whenever the C++17 contiguous iterator concept will be in, we probably have something that say, whenever you pass a range of contiguous iterator, you jump back to actually calling a load version of the compilers. Why do we need that? Actually, we had a fun side effect with some of our users that wanted to vectorize code that was processing data from a std list. Don't ask me why. Okay, they had a list of whatever, double, I think, or something. And they wanted to vectorize whatever operations they were doing on this list. And well, the best way we find out was to actually being able to say, okay, give me 2 iterators over your list, just load it into a pack and do whatever computation you need. We also have explicit load functions that can take a pointer and an offset, and we perform an unaligned or aligned load at these memory pointers with an offset. The offset itself can be a pack of integers, and in this case, we will just perform a gazer. So we will pick up data from different points in memory, starting from PTR, and gather them up into the vector. And you can use a masked load using the mask PTR type. That's an error type that you can actually build from a pointer and a condition. And you will load only the part from the pointers where the condition is true. And you can also pass an optional default value when it's false and so on. So it exists for a load and a line load. We have what we call a misaligned loads, which is basically a line. Well, it's a line load, of course. Sorry for that. A line load with a static offset. And that means that your pointer is actually not aligned, but you know by how much. It's not aligned by 1 or 2 elements, okay, something like this, or -1. And instead of using an unaligned load that could be costly on some system, we try to optimize a way to load this slightly shifted memory access. And we try to be faster than just calling the unaligned load. And same back, we have explicit function for store, again with offset, so we can do a scatter and with a mask, aligned and unaligned versions. So we have those explicit memory management. We wanted those to be explicit for a bunch of reasons. One is, the main one being that we don't really want to be going back and forth between the registers and memory without the users knowing it. So all the memory store and load, except for the constructor is something which is actually explicit in its own way, has to be explicit. So you actually can manage whenever you want to stop dealing with register and going back to the memory. Okay, so we put data into those packs. So we support basically every operators on those packs, all the standard language operators. We have a bunch of extensions. So for example, you are able to call bitwise AND or not on floating point values, because masking directly those floating point value with a mask is something you do a lot when you're writing a SIMD code. The only limitation is that we don't do conversion or promotion. So if you have a pack of char, one which is full of 255 and one full of 1, if you do the sum, you end up with a pack full of zeros. Okay. We got 2 kinds of comparisons. So you have the operators that perform SIMD comparison. So you end up with the vectors of Boolean somehow. But the number of Boolean as a result of those comparisons has to be equal to the number of data you put into the first one. So you cannot just have a pack of bool because you won't be able to know how many bools you need to store. So we use this logical of T type, which is basically saying, yeah, I'm encapsulating a Boolean value that is the result of an operation on something containing T. And we go back to the correct width of the vector using the T instead of the logical of T. We also have what we call reductive comparisons, so compare equal and compare less, that basically tell you if every element in 2 vectors are equal or if they are correctly ordered with the lexicographic order. So usually you want to do this in the middle of your computation, and if you want to stop when something is actually requiring a bool, you need to use the other ones. Pack is also a random access range. You can do a begin and end on it, and you will iterate over the scalar element. I'm not advocating doing it too much because it's a bit slow, and you can have random access to the value which return the proxy type to access to the actual register internal value. So you can actually write code like, basically like pack is a small array, except it's optimized in its storage and its operation. And you can do whatever kind of operation you want on that. And whenever it's possible, you get the SIMD version of this operation. We also have a bunch of functions, 360 something, that cover all the basics from arithmetic stuff, bitwise operations, some EIII operations, a bunch of predicates. We have a large selection of trigonometric function, exponential, and so on, which are pretty much already ready to use. We have a bunch of reductions, so we can ask if any or none elements in the pack verify the predicates, compute the sum, and so on. And we have a large subset of functions that deal with what we call the swap operation, which is manipulating the data inside the vector, including the very helpful shuffle function and stuff like group split and combine slice that can slice or aggregate vectors of a given size to give you a bigger or smaller vectors with keeping or not the output width. So combine and slice, basically, you take a pack of Tn and you get 2 pack of Tn over 2. And with split, what happens is you have a pack of Tn and you end up with 2 pack of Un over 2, where U is the type which is slightly bigger than the one you have before. So you go from a pack of 16 char to 2 packs of 8 shorts. So that's something you can use to do casting and stuff. Oh yeah, and we have what we call splatted reductions, which is basically computing a reduction, but instead of giving you a scalar, you get the same value everywhere in the vector, which can be helpful to optimize a bunch of cases. So what I say is a very funny operation is the shuffling operation. So reordering data inside the pack or inside the register in SIMD mode is very useful because you can turn your memory access and so your memory bound code into something which is actually turned into computation somehow. So you can actually write SIMD transposition, conversion between formats and so on, which is very useful. So we have support for what we call the specific permutation that is usually mapped to a direct intrinsic. So you can flip your vector, you can broadcast a value inside another one, you can interleave and disinterleave values. You can repeat a part, you can slide the value inside, and you can do what I call runtime lookup. So you can have a vector and a vector of index, and you will at runtime reindex the vector. But the most fun one is actually the shuffle function that supports arbitrary permutation, and that get optimally generated if the permutation is known at compile time. So you end up with a function that looks like this. So let's say you have 2 packs, okay, A and B. And you can write stuff like this. So I want to shuffle A using this permutation 0033, which basically say I'm returning a vector that contains twice the first element of A and twice the last one. So I end up with 1144. You can use a special value -1 to say that I want the zeros there. So some SIMD extension set has a special intrinsic for this, some don't. So we just wrap everything there and the optimal code is generated. So I'm taking the first element of A, I put 2 0, and I take the element 4, which is basically the first element of B, which is 10. So you can actually put whatever permutation you want there. There is one limitation of this syntax, is that the permutation is a variadic list of integers, so you have to know how many elements your pack contains, which is good for small toy example, which is probably not cool enough for actual code where you want to write code which is independent of your pack width. So we provide 2 other ways to do this. So the first one is to actually write a meta function that takes integral constants and return a computation on this integral constant. So the first one, I, is the index of the permutation you are computing right now, and C is the width of your vector. So this is basically a reverse. Whenever you've got I and C, I'm giving you C minus I minus 1. And you can pass this type directly as a parameter to shuffle, and you get your shuffle done. It's a bit better. Don't have to care about the size of your shuffling. it's still a bit cumbersome because you have to write this kind of non-natural meta functions. So another way to do this is use a const expert function. It starts to be a bit better. So you write your permutation function like an actual function, and you just have to wrap it into these pattern types and pass it to shuffle. And we basically do what it says, compute whatever indexes from there and shuffle it. So why do we need a pattern there? You have to thank Visual Studio for that. As I say, we support, yeah, sorry. Is James anywhere? No, it's okay. No, okay, so as I say, we support size 1 pack, even if it looks strange. And the problem is, if you write shuffle of 0a, Visual Studio is confused because 0 can be an integer, or it can be a new PTR conversion to a pointer to this function. So it doesn't know which one to take. All other compilers pick the correct one, which is picking the integer. So we just wrap the things, and everybody is happy. So what happens when we do this shuffle? Well, depending on the patterns you pass there, and your hardware, we can recognize a bunch of permutations that actually maps to something which is better than just calling the whatever basic shuffle functions. So if you happen to actually do this, okay, and you are on a system where you have an intrinsic to flip your pack, we will recognize that's a reverse, and you will call the correct intrinsics. If we fall through all the cracks that try to recognize special patterns, then we call the basic shuffling function. And if we fall in the cases where it does not exist for the type you want or for the size you want, we just do the permutation by hand, element by element. But you can actually use shuffle everywhere, and we will map it to the correct intrinsics just behind your back at compile time. Okay, so we also have this standard library integration. So we have a bunch of algorithms, transform, reduce, that use generic Fractal or lambda to process both the scalar and SIMD slice of the data. We have allocators, so you can actually allocate memory with a proper alignment constraint and so on. And we have a bunch of range that take a range of contiguous memory and turn it into something that can be used directly to get access to the data in a SIMD way. So the input and aligned input range basically turn a pair of pointers that describe a range into something that when you iterate over it, the dereferencing of this iterator coming from this range just gives you the pack that was loaded from the correct memory location. And then we have the segmented range, which actually takes an arbitrary range of contiguous memory, and it returns you a tuple of 3 elements. The first one is a range from the scalar value that you need to process between the start of the data and the first location in the data where vectorization is possible with respect to size and alignment. The second part of the tuple is a range which is basically an aligned range over all the data that can be vectorized. And the last part is whatever scalar values is left after the end of the last point you can vectorize. And so you can just take your pointers, get into a segmented range, and you get your tuples, and you can decide what to do on each of the sections. So you can use the algorithm like this. So we use a polymorphic lambda there just to do this p times 2 over all elements in this. So transform take care of knowing where to call the lambda in scalar or SIMD mode, and those all the prologue and epilogue and so on. And you can do the same with reduce. So you have the simple reduce like this, where it's basically computing the sum in SIMD mode. And sometimes you need to pass a more complex operation to the reductions. So for example, we compute the sum of the squared value. And in this case, sometimes you need to pass additional information. You need to specify the identity element of your operations, which may be different than from the initial value. And you need to pass a function which is actually the function you will use to complete the reduction. Obviously, you cannot call a plus e squared at the end of the reduction, because if you do this, you will square the sub-result 1 time too much. So we need to use plus. Bonus point, every function from BooSIMD is actually a function object, and actually a polymorphic function object, so you can just show them directly into algorithm like this. Okay, so how does all of this work? So we take a bunch of time actually looking at some details of the implementation that I think are actually interesting on how the C++ 11 and 14 helped us. So let's go back to some piece of code. So as I said, we implement our function actually as function object, except for the very obvious template function that needs to be template. And for doing so, we use an internal library which is called Boost Dispatch, which is a thin layer that helps us building function object using tag dispatching inside. So we use tag dispatching to select the best optimized version of function depending on the function argument types, classical tag dispatching stuff. We also pass a category that represents the current hardware specificities. So we know at compile time that we are compiling for something that has fundamental behavior like SSE or like AVX or whatever. And we pass another information, which is the fact that we categorize the function itself. So we know that plus is an element-wise function, so we can use it in place where you want to have a data parallel element operation. We know that sum is a reduction that use plus as its binary operator and 0 as its identity element, and so on and so on. And this defines the entry point of the function. And whenever we want to add a specialization for a given architectures or a given bunch of types, we have a system that basically say, okay, this is an overload for plus. I'm working on a machine that supports something that looks like SCC1, and my two parameters are packs of single precision values that are stored using the SSC representation of vector registers. And well, when I know that I can just call add plus ps and it's done. And same for if we go to, I don't know, what is that, AVX2. So if I'm an AVX2 machine, I got two int64 elements coming in and they are represented as AVX register, then we do this. So it looks like a redundant information to know which architectures I'm compiling for and which representation of register I use into the pack. In fact, it's not, because you have a lot of SIMD extension sets that has either multiple representation, that's the case, for example, for Neon, or in the case of AVX and AVX2, you have AVX extensions that bring you new operation on the SSC register. So we have somewhere, I don't know, we have a overload for function on AVX machine, taking SSC registers and using a specialized AVX operation on SSC register. And we have a pre-built list of, as you can see, different categories for all the basic types that we can use to do this. And this tag dispatching allows us to be able to, at fine grain, select what kind of code we want to generate, depending on a lot of operations. And I spoke about the fact that we have this information about the properties of the function. So like plus is an element-wise function, sum is a reduction, and whatnot. And that we use this information is what we call fallback overloads. For example, probably this one? Yep. So I said that, for example, you can write, you have two packs P and Q, you can write P plus Q, but you could also write P plus 4, okay? But we didn't want it to be able to force to write every operation with a scalar on one side, on the other side, and so on. So what we do is we say whenever we have an element-wise function, whatever the functions, and you call it with a scalar and a pack of whatever types. Okay, so what I do is I'm taking the scalar, I'm turning it into the proper pack, and I'm calling back myself on this pair of pack afterwards. Okay, Q, auto, delta type, black voodoo magic stuff. But yeah, basically we do this, and we can do that for, we do it for 2, for 3, and so on and so on and so on. But we never care about the actual functions. We also have a way to do something which is a bit more complex. Okay, whenever you want. Okay, well, I was thinking about being a bit more complex than that. So sometimes you end up wanting to call a function on the pack, but your architecture doesn't have the function. but you really, really want to call it. So what we do is we go into a fallback mode where we say, okay, I don't know how to do it using an intrinsic, so I will just compute everything pieces by pieces as a scalar values. So we end up with this element-wise overload to say, if I ever have an element type function that is used on CPU, which is the most highest level architecture's category, which means you are just on the CPU, I don't know what to do, and you have a pack of whatever in whatever quantities. Well, I will just give you a run on that because it's quite a bit of useful code, but basically we check that everybody has a correct size, and depending on the number of parameters, we just end up rebuilding the pack containing the function applied on every scalar values up to some amount of arguments, probably 4. So this way of categorizing the function properties help us doing this kind of global filling up fallback functions. So we also have this category hierarchy things going on for shuffling. Shuffling is actually very complex if you really, really want to capture all the crank and specialized shuffling. So let's start simple. If you have a width of 2 and you want to shuffle 2 vectors of 2 and you want to take into account the -1 cases, you end up with 3 as the power of 2 shuffle cases. That's 9. Okay, 9 cases, I can probably write all of them and specialize all of them. Now you get up on a 4-element shuffle. So that means you have 5 different values, okay, and if you do a binary shuffle, that means that you have 5 as the power of 8 cases. It's already too much, I don't even know how much it is. And one of the most interesting types usually is the 8-bit chart because that's the largest vector you can have. So you can have 32 elements in a vector of char on AVX, and if you want to shuffle that, let's say it's a unary shuffle, you get 33 as the power of 32 permutation, and I'm not gonna specialize all of that. Okay, I don't even know how much is that. Can I actually compute this? I mean, okay, so I say what? That at the power of this. Yeah, far too much. But if we think about it, there is a lot of cases where we can actually find an analytical way of finding what we should be doing. Because, for example, let's say you write a generic shuffling, but which is actually, in some cases, fall back to being the identity pattern. So you shuffle everything in place, 0, 1, 2, 3, 4, 5, n. You don't really want to call shuffle on that. You just want to return A0 directly. Or if you find a way to write a shuffle that happens to be a broadcast, you want to call the broadcast intrinsic. Broadcast, identity, reverse, interleave, disinterleave, a lot of these actually follow a formula. You can actually compute for a given size, and you know if you are in these cases. And so what we did is actually use metaprogramming to say, okay, let's try to find out if your permutation is a broadcast. It's a broadcast if all the value of your permutation, all the PS, are actually all equal together. So what we do is that we build an integral list of PS, and we check that everybody is equal to the first one. Okay? If this is the case, you are a broadcast. And if I'm a broadcast, well, I know that if I want to broadcast something, I just need to take my vector and call the broadcast function with a proper index. And what we do is, whenever we find out that your pattern hierarchy is actually broadcast, okay, we find out which index you need to broadcast over. Okay, and when we have this, we just be going into these broadcast shuffle cases where we do the proper things. And we do that for, as I say, broadcast, identity, interleave, repeating, reverse, and sliding, that all known to be able to be written differently than a shuffle. Okay, so all of this too much as a power of far too much permutation, we remove the bunch. Okay, but we still have this big bulk of them. And in this case, what we use is what we call we compute what we call the topology of the shuffling patterns. The topology of the shuffling patterns takes your patterns of permutation and try to know if it fits into the constraint of your hardware shuffle function. Which means that, for example, I don't know, is somebody there familiar with the SSE2 shuffle functions? So the shuffle function in SSE2, you take two vectors and you have to shuffle them, but the first part of the output must come from the first vector and the second part must come from the second vector. So what we do, for example, in checking the topology of a permutation, if it's compatible with SSE2, we write a meta function and say, okay, I'm looking at your patterns and do you fit into this? And if the answer is yes, this is the value you need to pass to your shuffle function. So it basically looks like something like this. So, yeah. So we have a 4 parameters permutation. And basically we do the, we compute the fact that oh, it's okay. Is my permutation index ordered correctly? Or are they ordered but the other way around, which means that instead of shuffling A and B, I would be shuffling B and A. And if it is the case, I will give you this information about what to do. Either you have a direct permutation, or you have an indirect one, or you have a regular patterns. And what we do into the shuffle, where is it? It's there. We say, okay, where is it? You're telling me you have a binary shuffling to do. Give me the topology of this shuffling. And either it's a direct one, so I will just call shuffle with a proper mask. Or if it's indirect, I will just call shuffle with value permutated and the mask. And if not, we fall back to the default matcher. So we use all those metaprogramming tricks using validix templates to how to split out how this shuffle is done. And in the end, we'll just go there quite fast. We end up with something that we know generates a proper intrinsic. Last funny stuff, is just before I go to something more interesting, is how we write reduce using segmented iterator. You want to process a range of data in an SIMD way, and you want to take care of the prologue and the epilogue and so on and so on. Well, that's 5 lines. We start by putting a 0 in the pack, we segment the range, and we just have 3-4 range over the 3 subtuple. And so the first and the last one, we deal with the operation using scalar, and the middle one just use the SIMD accumulator to accumulate inside, and we just return the sum of the scalar plus the sum of whatever is in the pack. 7 lines. I told you at the beginning that this is the first rewrite of the old boost SIMD. The old boost SIMD reduce, we don't have the range stuff and whatnot. It was probably around 80 or 90 lines and probably get full of bugs. And this range abstraction is actually very interesting for us because, well, what happens if we have another kind of reduce done? And transform is a bit more complex. It's basically the same idea. We segment the input, we process a bit, and we know what's going on. So let's have a look quite fast. Normally I did my homework. Yes. I'm just taking 5 minutes to show you that. So, where is it? Okay, far away. Okay. So let's have a look at. Where is it? Shuffle. So we have this shuffle, where is it? Test. So basically we fill out some vectors and we call some shuffling on them, identity broadcast, interleave, and some random shuffle. Well, even the name is random actually. So let's have a look at how it's end up. Okay, so well, we fill out the vectors. This is a place where basically there's a first shuffle, which is actually no shuffle at all. So we just move APS stuff. At some point, I do a broadcast. So where is it? Yeah, and the broadcast gets, in the case of the floating point, we get turned into a V shuffle using the broadcast mask 5.5, which is using exactly the same stuff. And for the short vector, because it's a bit more complex, but basically shuffle with a pattern, and then we shuffle back to the low and high parts. So we get that. And then we have an interleave that just ends up calling unpack directly. Okay. And the, where is it? The random shuffle, which is called shuffle B directly with the proper constant, which is read from these places. So yeah, we are able to generate that. And if we look at what happens for SSE, we get a different set of intrinsics. So probably this is probably better as it is. Okay. Okay, thank you. That's very helpful. Okay. Yeah, better. So same thing. Identity shuffle with 055 for the broadcast. Again, unpack. And a different way to doing the other shuffle, calling the SSE shuffle instead of the other one. But everything gets down to this. Okay. So we are able to generate these kind of things. So I'm going back to the slides. Just going over a bunch, very quickly, a bunch of tests we did, or people did actually. So I usually got the comments that we do some benchmarks, but we wrote both of the basic version and the BooSIMD version. So, well, I decided to fetch some benchmarks that was not written by us. So, should be better. So let's have a look, but first let's have a look at something we wrote ourselves. So I spoke about having, exponential, trigonometrics, and so on. This is the kind of performance we got. So it's computed in number of cycles to compute one value. So for the SIMD stuff, if you want the actual latency, you have to multiply that by 8. But in the end, whenever I want to compute an exponential, the cost in cycle to compute one exponential into my pack is basically 7 cycles. And we spoke about the fact that our functions are object functions. That means that I can pass them as parameters to other functions. And we have a set of stuff we call decorators, like restricted, that you can apply on an object function from BooSIMD to change its behavior. And restricted say basically your function there has different behavior depending on its input range. And I want you to use the smallest one possible. And if you get outside of these regions, just return none. So if you want to compute a cosinus, the regular cosinus, okay, you got this speed, okay. And if you want to compute a cosinus, and you know it's between like minus p over 4 and plus p over 4, you can use the restricted versions, which go far faster because it doesn't have to deal with all the other code paths for handling the other values. So we can get at this level of performance on this kind of operation. It's not perfect for some, but it's actually getting there. So I obviously have to have the stupid fractal example into these slides. If not, like people may think I'm not doing anything in parallel, so whatever. Yeah, well, it could have been matrix product too, but whatever. So computing this fractal is actually funny because it's largely compute bound, so you can actually see if you're doing things right or not. So the code is actually rather simple. You take your A and B, which is your complex part, your complex value, real and imaginary parts. We need to compute a number of iteration in res. So we have a bunch of meter function aliases that give you a type t and you turn it into an integer. And so we do the computation. And the problem is that this computation has a while. So vectorizing it needs some kind of tricks. So what we do is the usual tricks of computing a mask over all the value we computed and keep iterating until everybody into the pack converged, masking the ones that already converged. And what we do is that we only increment the iteration counter res if and only if mask is true. And we have this half computation, half control function like if inc, which are conditional operation using a mask over a pack. So this is the code, okay. Funny things, every BooSIMD function also works on scalar, so you can actually take this very template function and call it on scalar too, and you have the scalar version over that. I'm quickly finishing. So instead of running my own benchmark, I got a paper from Agnes Pohl from TU Berlin last year at WP MVP that actually compared a bunch of stuff, including us. So you have Circle, SIMD, GCMD, SAPC, OpenMP, VC, and whatnot. And well, we are doing quite well most of the time. The funny thing is that sometimes we end up having better performance than actually using the intrinsic by hand because we let the compiler actually change the way we want to allocate the register and whatnot. So we got a speed up of something around 3 something on SSE4 out of 4 and 6.9 out of 8 on AVX2, which is not bad. Mario Molinsky wants to use BoostCMD with Boost ODE int to vectorize the ODE resolution of a Rossler systems. You can get all the details there. Basically, the code is largely unchanged and we get 3 times faster. So this is the code that do the stepping into the ODE int. And upstairs is the Scala code, and downstairs is the BoostCMD code, where basically you replace the double by a pack of double. And we get 3 times faster. On these kind of systems using an AVX machine, double precisions. So conclusion, because I'm already out of time. Well, we wanted to be able to show that you can actually write C++ that looks like modern C++. We got templates, we got const expert, we got ... So we check all the boxes. And we can get decent performance. The code generated is most of the time basically what you will write by hand. The range and the iterators, the algorithms, items are very useful because you can actually piggyback them into SIMD and get a very nice looking code. So something changed, because I did some similar talk a lot of time, but we have a release, like yesterday. It also happens that we have an actual documentation. So everything is on this GitHub now, and as soon as I'm going out, I'm just trying to find Robert Ramey and probably Michael Kess and try to call them to start the review as soon as possible. So someone on IRC channel of Boost once made a joke about the fact that 2016 will probably be the year of Linux as a desktop OS and the date where BoostCMD is actually released. So yes, it's done. So you're free to download that, test it, get feedback. We got a bunch of forums, issue tracker. I really appreciate it if you are dealing with a very specific domain of computation that we do not know, and you got strange bugs, strange performances, and you want it to be better. I also want to thank a lot of people, so the BCD team from Numscale, and a bunch of our earliest supporter and adopter, Tim Lenchman, Serge Guelton, which is including BoostCMD into Python, Mario for its work on BoostCMD and BoostODE, and some of our co-workers and students that are actually testing BoostCMD every day. Thank you and sorry for having you over time. If you have any questions.